SPDE.
Okay, thanks a lot. First, I have to say I'm happy that there is actually an audience. I was a bit worried about this being Friday afternoon and the last day, but this seems to work well. And, well, the plan for the talk is still this being Friday afternoon, that I do everything as simply as possible, so I restricted all of this to just the bare bones necessary for you to require what I want to explain. So I'm cheating a bit, as you hopefully will not notice, but you may. But so the plan is this is all very simple. And what I'm going to do is I'm talking about Burger's SPDE and about how to discretize the thing using finite difference methods. So finite difference approximations of SPDEs, and SPDEs here means for most of the talk just Burger's equation. And this talk is a bit strange in that it's not a talk about how to discretize an SPDE, but it's a talk about how to not discretize an SPDE. Namely, the main result is if you use finite differences and are not careful when doing so, then things can go badly wrong. So what I will do basically is show something which can go wrong and where you need to be a bit careful if you try to use finite differences with an SPDE. So the whole purpose of the talk is to illustrate this effect. Okay, there are 4 parts. The first one is very short. I just want to remind you about stochastic Burger's equation. And, well, so this is the main part. So there I will explain what can go wrong if you use finite differences. And then I will talk a bit about how to generalize the thing. And this is the other thing I want to put the focus on in this talk. In Burger's equation, you can have viscosity and noise, which are 2 parameters you can play with. And I want to talk a bit about what happens if both of them are small.
Is that a typo or a joke that you with an element instead of differences?
Oh, this is a typo. This will probably reappear at the section title since later. So elements, it's differences. Sorry about that.
What you're saying is finite differences are bad.
It's all finite differences. There are no finite elements in this talk. Yeah, I apologize for this typo. Okay. So stochastic Burger's equation, I guess I don't need to say much about this. So it's just very standard form. So we have here second order term which tries to make everything smooth. And this parameter nu here is, well, one of the parameters I can play with. The W is meant to be a cylindrical Wiener process, so the whole equation is with space-time white noise, so very rough. And this noise which makes everything rough and Laplace operator which makes everything smooth kind of balance each other. And this is what makes the Burger's equation. This is a transport term, obviously, which shifts everything, and the speed is proportional to u, which means if you're positive, it's shifted to the right, and if you're negative, it's shifted to the left. And, well, so I said these 2 terms balance, so maybe the most interesting thing is how do they balance? The answer is the solution looks a bit like a Brownian path, also as a function of space. Namely, it's in the Sobolev space h1/2 minus epsilon for every epsilon. And now, yesterday in the talks, I learned every good talk has a movie. So I thought the best way to explain Burger's equation really is to just show you what it does. So this is how stochastic Burger's equation behaves. You see it has noise in it. You also see it moves to the right. And it's to the right because you see here I didn't start it in a centered way, but I just started it a bit positive. So that everything moves to the right. And you also see the effect of the smoothing out term. Well, first, it doesn't explode with the noise, but also I started with something which was shaped like a sine. And you see as this progressed, the peaks kind of leveled out. And, well, so this is the object I'm talking about. Yes, so there it is. And now there are several things. So the equation I wrote down for you is just with this viscosity term nu and with the noise term sigma. But you know there are already problems with stochastic Burger's equation when these terms are not present. And since I want to talk in the end about small noise and small viscosity, I've just collected some things which can go wrong. So let me just go back to the equation. So this here is the viscosity. So the question is what is if the smoothing term is not there and no noise is there. And the results, this is all well known for a long time. So this actually needs a bit of care. Namely, if you do finite differences. Actually, they only work if you do the differences in the right direction. So you could do left-sided derivatives, left-sided discretization of the derivative in the nonlinear term, or a right-sided discretization of the derivative in the nonlinear term. And it turns out you actually need to be careful, namely it's unstable if you do it wrong, and where the solution is positive, you need the left-sided discretization, and where the solution is negative, you need the right-sided discretization. And even if you do this right, it's still a bit strange, namely the solution has shocks. This means discontinuity is in the solution, and if you think about the equation again, this is very clear. The speed of propagation is proportional to how big you are. So if you start with some hill-shaped thing, the top just moves faster than the lower regions, and so it kind of like a breaking waves topples over. And so I have another movie. So this is without noise and without viscosity. So it's just the transport term, and you see after a while you see these shocks. So it kind of has a discontinuity there. And well, this was one of the two things I said. And the other thing that you need to be careful with the discretization. I have also a movie about this. And what happens is the solution is just unstable in the sense that the high frequency modes blow up. And they blow up very quickly. So this thing is actually a movie, but it runs in very slow motion. So you see the time here. And it's so slow you can't actually see the propagation. And then it runs a bit. And well, so you see this is, if you don't use the correct direction of discretization, it goes wrong nearly immediately. So the time run, let's just do this again, it run until 0.0 something or so. So, well, you need to wait a bit, but you see it doesn't even reach 0.01, and the other simulation I showed you was up to time 2 or something like this. So, well, so there is this instability, and all of this is well known, but it's something where you need to be a bit careful already. Okay, so we have these two problems, and again, these two problems are also if there's no viscosity. So the viscosity smoothes everything out, which makes no shocks being there and removes this problem with the one-sided discretizations. And well, so the noise makes things worse. So I showed you the thing without noise, which was kind of the better situation. Okay, so this is Berger's equation. And now, how do we discretize this? So I want to use finite differences. And if I just go back to what I showed you, so finite differences, this is the slide where I explained that you can do it wrong. So you can discretize this derivative left-sided or right-sided. And of course, you could also try centered, by just taking ux plus delta minus ux minus delta and then divided by 2 delta. So there are different choices, but we see already they may make a difference, at least if there's no viscosity. And so what I do here is to just cater for all of this. I just write A for how much we go to the right, and B for how much we go to the left. And then if I divide by A plus B times the step size, then, well, it will be some approximation to the derivative. OK, and again, if we do it without viscosity, we actually want A equals 1 and B equals 0 if the solution is negative, and A equals 0 and B equals 1 if the solution is positive. And we never want the centered thing. But, well, if viscosity is there, maybe the centered thing would be a good idea. This would be A equals 1 and B equals 1. OK, and without noise, it's just standard numerical analysis. So if the viscosity is there, so I have the nu in the equation, then it doesn't really matter what you do, whatever you choose. It just converges to the right solution. So this is good. So you can choose whatever you want. And the point of the talk is the thing which stands a bit innocently there down on the slide, namely with the noise. So if sigma is bigger than 0, this doesn't hold at all. So things go badly wrong. And only for the centered discretization, this is the only exception where it goes right. And yes, so let's go there. So I'll explain in a minute what goes wrong. But here's already in first illustration that things are a bit strange. This is the Berger's equation with the same noise solved 3 times, but with right-sided discretization, left-sided discretization, and centered discretization. And, well, you see I just get very different curves. And no parameters are degenerate. I just set all parameters to 1. So sigma is 1, epsilon is 1, and I solve the whole thing to time 1. And the space step size is really little. It's, I don't know, 10 to the minus 5 or something like this. And so the only thing which is different between these three simulations is, again, if a equals 1 and b equals 0, the top curve corresponds to the case where it shows a right-sided discretization of the derivative, the middle curve centered, and the lower curve a left-sided discretization. So again, I did the thing here with the discretized derivative, and only these a and b are different. And we see already, obviously, something is strange. These seem not to converge to the same solution. So, well, something is going on here. And what I believe is what's going on is written in the following conjecture. Namely, so just a reminder, the delta is this way of approximating the derivative. And the conjecture says, if I solve the equation where the derivative is replaced by this thing, and let the step size delta go to 0, then I do converge, but I converge to the solution of this SDE, which starts out as Burger's SPDE does. So it's second derivative times nu minus the nonlinear drift term, and here's the noise. But you see, the limit actually has this additional term in here. So the conjecture basically says finite differences does not work for this equation, except if I set a equal b, then this term isn't there. Yes?
There's a big difference between the one-sided differences and the center difference. Namely, you get a higher order approximation of the center difference, right?
Yes. But it turns...
And you're using a second-order scheme, I suppose, to move upward.
Yes, but it turns out that this is not what's going on. Namely, there are non-symmetric second-order schemes where you just go 2 grid points to the right and balance the coefficients properly. And there the problem also occurs, so it's not the second-order thing which makes everything good.
Symmetry?
Well, a bit more. In reality, it's just some regularity in a bit more abstract sense, but it seems to be closer to symmetry. But OK, so the plan for the talk is we want to understand this thing. So first, this is pretty bad because I do lots of simulations, and very often kind of there's no theorem which tells you that it does work. And what I do is I make the grid a bit finer and see whether it explodes or whether it kind of stays the same. And if it stays the same, I hope everything is good. Whereas here, you see, it does actually converge. So this hand-waving test just horribly fails. So you will never notice by just doing it that you converge to the wrong limit. And
Jochen, is that a number?
this thing here?
Yeah.
And yes, it's a constant.
So just a constant.
So it's a constant drift which acts all over the thing.
Spatially homogeneous.
Yes, 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 exactly. And OK, I should say this now. A few things. Namely, first, this talk and also the paper which the talk is based on is free of proofs, nearly. The talk entirely free of proofs. So what's happened is we have some conjectures here, and we have numerical evidence for them to be true, but we do not have a proof. And
The numerical evidence was what you showed in the
no, the numerical evidence is what I will show in 10 minutes.
Do you mean there is no DT theorem or?
There is a DT here. I forgot to write it only. OK, and the first plausibility check. So if we take the right-sided discretization, then A is 1, B is 0. So this term here is, well, as Gabriel already observed, it's just spatially homogeneous. So it's the same everywhere, and it's positive. So the right-sided discretization we expect to be bigger than the centered one. And if I go back to the picture, so A equals 1, B equals 0 is the blue curve, centered is the green curve, so it actually is bigger. So this works well, but I will show you way more convincing evidence in a second. And so this was one thing, so we check this with numerical experiments. And the other thing I should say is you can get around this by being just a little bit more clever. So this here is more an effect we study because it's interesting in itself and to learn where you need to be careful. But for this specific equation, well, the drift term is u times derivative of u. So if you write this as the derivative of u prime, then everything looks a lot simpler. And actually for the theory, if you plan to prove that stochastic Burgers equation has a solution, this is the way to write it, to do these proofs. And actually it turns out if you write it like this, then the numerics get a lot happier and the problem just disappears. So this problem, it's not a problem as in we can't solve stochastic Burgers equation, because we can if we just, again, write the nonlinearity as derivative of u square and then just discretize u square. In some ways this will all work, but it's just a warning if you do it in the not so clever way, what can go wrong. Okay, and now two parts, namely first I will give you a hand-waving argument which explains why we think this additional drift term is sigma squared over 4 nu. And then the second part is numerical experiments which show that actually if I try it, this works out very well and is in good agreement with this. Okay, so first the heuristic argument. The heuristic argument is, well, it's obviously caused the problem by the roughness of the solution. So, well, if the noise isn't there and the solution is smooth, we know we converge, so it must be caused by the solution being as rough as the Brownian motion also. And what we do is, for the argument, we consider another simpler process, namely just stochastic heat equation, which doesn't have the transport term in. And this thing, of course, it's a different solution, but this will have the same regularity as the solution of Burgers equation. So we can use this to see how rough the solution actually is. And now this is a linear SPDE, so this can be easily solved. The easiest thing you can do is you just take the eigenfunctions of the second derivative operator, and we have periodic boundary conditions here, so these eigenfunctions are just e to the INX, and then just write everything in Fourier modes and look what happens to the nth Fourier coefficient. And of course, this is very simple. So the zeroth Fourier coefficient is the constant function. This doesn't act on it, so only the noise acts. And this I wrote here. So the zeroth Fourier coefficient, if I get the constants right, it's 1 over square root 2 pi, so that's the norm is 1. And on this coefficient, I just have a Brownian motion acting. And the other coefficient, of course, you just get an Ornstein-Uhlenbeck process where the drift is like minus n squared. And if you sort out all the constants, you get the other coefficients e to the INX over square root 2 pi. So the prefactor I can write like this, where in the psi n I collected everything which is random. So the psi n is an Ornstein-Uhlenbeck process, and I normalize them all that they have all variance 1 in the stationary distribution. And then the n dependence, I collected the terms all here. So it's I n square root 2 nu. And since the original process was real, there is some condition to make this real, and this is just psi minus n is the complex conjugate of psi n. So this is all very easy, so you can just work out what this is. And the relevant thing is that the psi n are all the same size. So variance is 1. These Ornstein-Uhlenbeck processes, so the coefficients, of course, decay like 1 over n. Okay, and now let's see, for a function of this roughness, what does our discretization do? So we need to compare the proper derivative to our discretized derivative. And proper derivative, if we just take it formally, let me just flip back a slide. So we have e to the INX, and we want the x derivative, so we just put in in front, which cancels this. This has no x and goes away, so what we get is, well, this here is the Ornstein-Uhlenbeck processes are still there, and the constant now no longer depends on n. And, well, so this was easy. Then the discretized derivative, so again, this is the function we have. Discretized derivative was we go a bit to the right, we go a bit to the left, subtract the values and divide by the difference. The only x is here, so if we go a bit to the right, we have INX plus A delta. If we go to the left, we have INX minus B delta. So here we are. If I just collect this, INX plus A delta is here, and INX minus B delta is here. And if I write it like this and pull out factors until the front looks the same as the exact derivative, I get this. So the question is this thing here close to 1? And if we look for a second what this actually is, so e to the INA delta, if here's complex Unix circle, and here's the real part, and here's the imaginary part. So e to the I n a delta, and here is e to the minus I n b delta, and I divide by I n a plus b delta. So you see this thing is close to 1 on scales where the circle is close to a straight line. So if this was straight up instead of bent, it would be 1. So this approximation can only work, we see immediately, if n-a delta, or n delta rather, is small. So the Fourier modes where n goes up to 1 over delta will be okay, and the higher ones, well, we just go horribly wrong, because this loops around and then gets very small. Okay, but these were only the derivatives, and in reality, of course, the drift is, let's write this, so it's u, dxu, and what I wrote so far was only this, so we need to pre-multiply by u and see what happens. And actually it turns out, so this thing here we can again express in the Fourier basis, and the whole problem happens already at the zeroth Fourier mode. So I just work out what's the zeroth Fourier mode of u times the derivative. Well, and for the exact derivative, I already said it, or here I wrote it with v, so v times derivative of v, of course I can write as the derivative of v squared, and then I integrate it, and it's periodic boundary conditions, so it just goes away, just because this is the total derivative. So this is easy. And let me switch back again. For the approximated derivative, I have this thing. So I have this thing and need to multiply this by v, then split it into Fourier modes and look what's the zeroth Fourier mode. Okay, and zeroth Fourier mode of a product I just get by the convolution. So I take of the v Fourier mode number k and of the derivative Fourier mode number minus k, multiply them, sum them up. And, well, if it was the same, this thing would be 0, and so we should look at this, whether it should be 0. If you look first, it just looks a bit long, but we can collect terms. So first the xi, these were Ornstein-Uhlenbeck processes, and I had normalized things, they are all of the same size. I mean, randomly the variance is all the same. So xi k times xi minus k, because xi minus k was the complex conjugate of this, turns just into norm xi k squared. And, well, all the constants I collect. So the interesting thing is there's a k here. And the other terms, well, it's trigonometric polynomials. And by combining every time a positive and a negative k, I can turn them into cosines, and it turns out to get cosine k b delta minus cosine k l delta over this factor. And, well, still doesn't look particularly like this thing could be 0. And it turns out actually you can compute what it is, at least in the limit delta to 0. So I just copied the expression. This is the expression which, if everything was fine, should be 0. But I didn't write here how you do it, but you can already see there are these deltas in here. And you can actually, and you are interested what happens if delta goes to 0. And you can rewrite the whole thing that it looks like a Riemann sum. And then if delta goes to 0, it actually converges to an integral, and it's not very difficult. You see, so k delta will then be x in the limit. So the integral this converges to has a cosine bx coming from the cosine k b delta, and the cosine ax coming from this term. And this stays, and k delta is an x, and k another delta would be another x, and the delta I just introduced here, I write here, which is the dx here. So this is quite straightforward. So this thing, if delta goes to 0, converges to this integral. So if everything was fine, we would need to see that this integral is 0, but luckily this one can actually compute, at least Maple can. And, well, the answer is this integral actually is this, which is not 0. And, well, if you remember what I did, so I worked out what's the effect of the nonlinear, or the 0 Fourier mode of the nonlinearity. And the answer turned out to be the 0 Fourier mode of the nonlinearity. It's a thing here, and the 0 Fourier mode remember, it's a constant function. So the nonlinearity, when discretized with the approximate derivative we just got with this bit heuristic computation, should have this prefactor. And this is why we think the zeros Fourier mode will this have as a prefactor. So we assume that, here's the conjecture, we assume there must be a constant drift of just this magnitude. So this is the heuristic argument. You see, I cheated a bit by just taking derivatives of v and stuff, but it's at least a way to get this number. And the rest of the talk basically is to give you a second line of evidence on top of this heuristic computation, namely, and try now to make this number visible in a computer program. Okay, so this was the...
Sorry, but this calculation doesn't rule out the possibility that a sufficient condition to get convergence to the right equation is that you just use a second order approximation of the derivative.
Oh, no, it does not. But you can do the same computation for different ways of discretizing the derivative. So, where was it? Here. So when I did the way I discretized the derivative went into this term here. And I didn't show you this, but you know, if you have now your favorite second order scheme, which happens to be not this, you can still plug it in here and redo the whole calculation. And it turns out there are second order schemes where you get a contribution. You know, I don't have the calculation here, but I'm telling you.
So the drift will be like slightly different, modified.
It's just some number again. Yes?
Number times h, maybe?
No, just like here, just a number. So it's not a second order thing. Yes, Jonathan?
So it was too quick for me to do this calculation in my head, but just if I had written it in flux form, so by that I mean the derivative of u squared over 2, and I did center difference and right and left difference, would that have the same deficiency?
Sorry, say it again?
So if I wrote it in flux form, if I wrote u squared and I took the derivative of that, right?
Oh, no.
Would that have the same deficiency?
No. You mean just sitting?
Right.
Yes, and now the problem disappeared. If you, disappears
Yeah,
if you
okay,
do
I
it.
didn't understand. Okay, well, that's what you were saying there. I didn't understand.
Yes. But
Yeah,
this is
okay.
what I tried to say.
Yeah, sorry, I misunderstood.
Okay, so again, we can easily fix this if we discretize u squared instead of the derivative of u. But, well, that's kind of not the point of what I'm telling you. Okay, so before I give you numerical evidence, so this is actually possible to check, but I thought I want to generalize this a bit more, and so I'll give you the numerical evidence for the slightly more general statement. So we need to wait for 5 more minutes for the next picture. So instead of Burger's equation, which has just u, derivative of u here, we could, of course, discuss other equations which have some function of u times derivative of u here, and try to do the same thing. And, well, you see conjecture 2 says if we do this thing, what we get is the solutions actually do converge, but they converge again to the wrong thing. So the limit is equation with the g of u exact derivative of u, some correction term plus sigma dw. And just to check, if g of u equals minus u, I get back Burger's equation. And in this case, g prime of u is minus 1, so I get plus sigma square over 4 nu. And what you see here, I only did the right-sided discretization. So from now on, I only have right-sided discretization, which is why the a minus b over a plus b is no longer here. But the point is, if we have a function g here, we also have a conjecture which tells you what do we expect as a correction term. And this is the thing I'm going to check. And you see, if g is not linear, then the correction term is no longer assumed to be constant as a function of u, but some function which actually changes. And I'm trying to verify this by designing an experiment where I can actually check for the functional form of whatever correction term is necessary, and we'll see there will be quite a good fit. And, well, there are quite a few fine points to this thing. So I wrote it in the one-dimensional case where everything is good. In the multi-dimensional case, things get a bit strange, namely the SPDE here. I mentioned this earlier. If you are going for Burger's equation to prove existence of solutions, one way to do this is, or probably the way to do this, is to use the fact that the u derivative of u could be written as the derivative of u prime, and this has kind of more obvious regularity properties, and you use this. And so in one-dimensional case, this g, of course, in one dimension is the derivative of something. So in one dimension, we can always write g is equal to h prime for some function, and then g of u derivative of u is the derivative of this function h of u. So one could use the same trick, but in higher dimensions, well, some functions are derivative of something and some are not. So this cannot always be done, and in the cases where this cannot be done, existence of solutions, or what it means to be a solution of this SPDE, is no longer entirely clear. But of course, the conjecture kind of still works. So the conjecture would, if I just change it a bit, if I discretize this thing in a centered way was good and didn't introduce an error, and this in a right-hand way, then I would claim, even if we can't prove that the thing here in the limit has a solution, we can still try the discretized equations, which are perfectly fine. It's just in high-dimensional SDE and has a solution. Then we could claim this thing where we can't prove that it has a limit gets more and more similar to the right-hand discretization of this, and this works beautifully even when we don't know, we can't prove that there is a limit. So this seems quite robust, actually. Okay, but now for the promised numerical evidence. So I have this thing discretized with a right-sided discretization, and I want to know what does it converge to. And I have this conjecture I want to test that it converges to a prescribed correction term. So what I do is I solve the thing we are talking about for small delta once and for all, and remember the solution. So I solve the, say, to time 1. And then I solve the downstairs equation with some known good scheme, for example, by using the trick I just said, that we write g of u times the derivative of u as the derivative of some function h of u or so. So we can find schemes where we can prove they converge. So I solve this thing, which I suspect is a limit with the known good scheme, and compare the numerical solution of the suspected bad solution to the known good solution of the modified equation. And this I can do for every gamma. Okay, and then the next step of the game is, now I would like to know which gamma is correct. So what I do is I play with the gamma, try different gammas, and try to find a gamma which makes the good solution of the corrected equation as similar as possible to this equation. So what I did actually was, for gamma, I chose a parameterized family of functions, so actually fifth order polynomials, and then I just did a multidimensional minimization to minimize distance between the solution with correction term from the numerical solution with the right-hand finite differences thing. So I just tried to minimize this by optimizing over the parameters of gamma, and so it was a fifth order polynomial. So I just optimized over the coefficients, and just numerically, so without any intelligence, by just running it often and taking some numerical minimization algorithm. Okay, and let's just flip back one slide. The conjecture was the correction term is minus sigma square over 4 nu times g prime. So if I do the minimization procedure and look for the gamma which makes the good solution of this as close as possible to the right-sided discretization solution of this, if it works, we hope that gamma in the end looks like sigma squared over 4 nu times g prime. So this is something you can actually check. Okay, and the result I'm quite happy with. So this is the outcome. So I didn't write this anywhere. So for the example, I took something just halfway simple function, which is not linear. So I took g to be sine squared of x. And I think it was sine squared. This green line is then the predicted correction term, so the green line is a bit hidden in the background. So this is just g prime with the correct prefactors and the minus. And the red line here is what I got from trying systematically different correction terms by using fifth order polynomials and optimizing and taking the fifth order polynomials so that the solutions are as close as possible. And you see the red line and the green line, at least in the middle, are quite close to each other. So that's very good. There's no perfect fit, but then the derivative of sine squared is just not a fifth order polynomial, so it's only this close you can actually get by this minimization. So these gaps here, I would just say, is I took a too small family of possible candidate correction terms. So we have quite a good fit in the middle, and why doesn't it fit at the outside? This actually is very easily explained, namely the histogram down there, the blue stuff, is the region of space the solution actually covers. And so I'll just switch back. So this gamma here, again, is in correction term, so it's only evaluated at values of u. And u actually takes only these values, so if I change gamma outside this interval, well, it will have no influence whatsoever on the solution, so I can't just have no way of seeing what it is. So this means, since outside here we didn't just use gamma, that this is a near perfect fit. So this thing here, again, I was testing the conjecture and was testing actually for the functional form of the correction term, and even not just the average value or so is good, but even the functional form that is big here and small here is quite well represented. So this, I would say, is strong evidence for this conjecture to actually be correct, because I just tried what function do I need to place here to make the solution as similar to this one as possible, and without putting in the conjecture, I got the red line when the green line was conjectured. So this I found pretty convincing.
Can you check the rate of convergence?
Of what to what?
Rate of convergence?
Of the discretizing to the wrong solution? We didn't even try, but I guess
The
it
wrong
will.
discretization to the wrong solution.
Yeah, but I mean, it will converge just like finite differences do, I guess. But we didn't try anything, so I mean, you know, it's not a usable method, so there's not much point, because it just does not work, so there's not much point in working out how fast it does not work. But if you can do finite differences, I guess it will just apply here. Okay, so, oh, I need to be very fast now. Oh no, I started 10 past. Then I can just progress at current.
Exactly 10 past.
Oh, then I can progress at current speed. So let's just switch back to the proper conjecture. So the conjecture here, the correction term, both in conjecture 1 and in conjecture 2, had this prefactor sigma squared over 4 nu, where sigma was the number in front of the noise of the S of Berger's SPDE, and the nu was the viscosity, the number in front of the second derivative. So one moment. You see, if sigma squared and nu are the same number, then, well, this correction term is assumed to be of order 1. And this effect should show up for arbitrarily small noise. So if we want sigma small but take nu small in sync, then we should still see the problem. Yes, you had a question?
For this more general case, what's the basic assumption of this function g?
To do what?
I think you have some basic assumption on this function g, right? I mean,
Careful. This whole thing, as I said, is a conjecture, so there are no proofs whatsoever. So I'm quite flexible with assumptions, but the numerical evidence, I mean, the numerics still work when we can't prove that this thing even has a solution. So for the conjecture itself, you know, G is smooth in some unspecified way or so, but as I said, it's not a theorem and not meant to be a theorem. So basically, I tried it for sine squared. Okay, so as I was just saying, the correction term is proportional to sigma squared over nu. So if we take sigma squared, same order of magnitude than nu, then the effect should stay visible even if I let go the noise, if I let the noise go to 0. So let's do this. Sigma squared, the same as nu, so I write epsilon for nu, and then I write square root of epsilon for sigma. Okay, so what about this equation? And of course, now I'm interested in the case of small epsilon. There are now two things to play with still. So there is this epsilon, which controls both viscosity and noise. And there is the grid size of my discretization, this parameter delta. And, well, both of them we want to take the limit to 0 eventually. And the point is we cannot do this in two different orders. So if, for example, we try first, we let epsilon go to 0, then, well, without the noise term there, we expect it to just converge to the, it's called the viscosity solution of the non-viscous Burgers equation. So it will just converge to this. And, well, with the epsilon here, one hopes that it still converges to this. If I let epsilon go to 0 first, and then if I let delta go to 0, I said this at the beginning, you need to be a bit careful. So you need to use an upwind scheme, else you have these instabilities, because now no viscosity here. But we hope that if we do the upwind thing, it actually converges to the right thing, so to the real non-discretized solution of this. The other thing we can do, we can first, in this equation, let the discretization go to 0. This is what I just talked about. So if I take right-handed discretization, we converge to this with the correction term. Now, the constant nu and sigma squared cancel, so only the 4 which was there is left. So we think we will converge as delta goes to 0 to the solution of this SPDE with the extra 1/4 here. And now if I let epsilon go to 0, again, one hopes this and this goes away, but the quarter doesn't depend on anything. It's just a constant which is there, so this will just stay. So it seems the two limits, if our conjectures are correct, just don't interchange. So if I let discretization go to 0 first and then take the epsilon away, I get non-viscous Burger with a 1/4. And if I let epsilon to 0 first and then the discretization step size to 0, I get just non-viscous Burger. So this is the effect I wanted to, well, try to make visible again. And this also worked quite beautifully. So we did a bit of hand waving to work out where's actually the boundary. And it seems the boundary is as easy as possible. So if you take these limits in a way together that delta is always a lot smaller than epsilon, the delta was the grid size, and you run into the situation from conjectures 1 and 2 before, then you expect the limit to be the thing with the 1/4. And if epsilon is smaller than delta, then you expect that. So this is the conjecture. There's a bit of hand waving why this may be right, but my plan again was write a computer program, try to actually see this effect. And okay, so how do we do this? This actually I was quite happy with how it worked out, but first the experiment is we have these two possible limits. So we have either non-viscous Burgers just as is, or with the additional 1/4 on the right-hand side. And I wrote it already here in this exact form. So of course, if you want to solve these, you better discretize the derivative of u square. And also, if you solve these, you need to be careful with the upwind and downwind thing. So I used an upwind scheme. So first thing is I computed numerically just solutions to these two equations. So there's no noise in there. These are the two limits I could get if I let both grid size and noise go to 0. So I have these two functions. Okay, and now I take a small epsilon and delta, solve this SPDE I was talking about, and I'm after what goes wrong if I take the right-sided discretization finite differences, so I do just this. And, well, I solve these until time t, solve this until time t, and just compare the solutions. So this, numerically, I just get some function. I have earlier computed this function, so I can just check, is this function I got from down here, is it closer to this, or is it closer to this? And, well, so this is easily done. Just takes a bit of time. And I thought a while about how to actually visualize this. So I want to create a nice picture of this. So as a function of epsilon and of delta, which is not in here, but which is the discretization step size, I get these two numbers. And I wondered how to plot these. So what I came up with finally is a way to map them into the plane. So we have distance from my solution to the first proposed limit, distance to the second proposed limit. Both of them, of course, the functions, all three of them live in Hilbert space or some discretized Hilbert space. But what you can do is you just have kind of a triangle. You know the distance u0 to u1. You don't know the distance from your solution to u0 and from your solution to u1. So what I finally did is I just mapped it into the plane. So I just drew a dot for u0 and a dot for u1, and they have the correct distance, which is just the same as the distance of u0 and u1 in Hilbert space. So this is not a schematic diagram, but actually with the scale and everything. And then once I have these 2 points, my solution u, well, if I know the distance to this point and the distance to this point, there are only 2 points where it could be. So if I want to map it in the plane that these distances are preserved, it could be here or it could be down there. And if I insist on everything being on top of this line, these 2 distances just determine the point. And the distances between the points in the plane reflect distances in Hilbert space. So this was a bit of a disappointment. I invented this and was very proud. And then Wikipedia knew about the thing and it has a name and everything. But whatever. So it's a way to just map our solutions from Hilbert space into the plane and to see whether they are closer to u1 or closer to u0. And, well, to conclude, so here's the result. I tried this now for different deltas and epsilons. And for each delta and epsilon, I get, well, a solution which I compare. So let's look at this point. So this point corresponds to delta equals 10 to the minus 4, and epsilon 10 to the minus 1. Then I simulated all of this and checked, is it closer to the solution with the 1/4 or closer to the solution without the 1/4? I computed 2 distances in Hilbert space, and then I mapped it in the plane by just putting on these 2 distances. OK, so I did this. And now I decrease epsilon. Turns out what happens is the distance to u1, solution with the correction term, gets smaller, whereas the solution, the distance to u0 doesn't really get smaller. So we move straight towards u1, both in the plane and in Hilbert space. And so what you get is these fancy non-straight lines. Namely, what happens is if I let epsilon to 0, so same grid size, same discretization, and I just change the thing which controls noise and viscosity, the solution first looks very much like it's going to converge to u1 until I cross, let me go back to the conjecture, I cross this limit. So if delta is big, I'm changing epsilon. If epsilon is big compared to delta, I expect the correction term to be there. So if epsilon is bigger than delta, I expect this to be close to the thing with the correction term. And one further, well, so we see 10 to the minus 4. So if epsilon is bigger than 10 to the minus 4, or much bigger actually, I expect this to kind of converge to u1. And it does. And then if I cross the 10 to the minus 4 line, then I'm in the other regime of the conjecture. This is if epsilon is much smaller than the step size. Then I expect suddenly to converge to u0, the thing without the correction term, and you see it kind of changes track. And right at the prescribed point, so 10 to the minus 4, where epsilon equals delta, we are here, and then suddenly it changes direction and converges to the thing without the correction term. And, well, so the different curves are just with different grid step sizes, but this I again found, I thought, was a pretty convincing argument that the conjecture actually says something true. Namely, if epsilon is bigger than delta, it really looks like we converge to u1, and if it's smaller than delta, suddenly it really looks like we converge to u0. OK, and this picture, when I produced it, made me very happy, and also I heard that numerical analysts always produce pictures with straight lines, so I can see I'm not a numerical analyst. These are not straight lines. And this is everything I want to say here.
Questions, comments?
This numerical tests are made with non-negative data or not? The initial you take to compute
you mean?
evolution equation, you take non-negative data or?
Oh, yes. Actually, I do to get around the upwind thing. Actually, I take negative data in the right-handed scheme, so it is upwind. But yes, I did this to stay away from this instability I showed you at the beginning. You know, it takes the initial condition to have the correct sign. And I run it for such a short time that it never changes sign.
So to be sure we understand each other, so you, for example, if you take non-negative initial datum, you take the wrong discretization.
Stop. There are several things, several ways it can be wrong. It can first be wrong in the way I showed you at the beginning with this movie where it exploded. So the standard numerical analysis is wrong where there's no probability involved. And there it just means you need an upwind scheme, which means negative solutions require a right-handed discretization, positive solutions require a left-handed solution. And this I did correct because I used the right-handed solution and a right-handed discretization and a negative solution, so this fits. But the other wrong is, of course, with noise, neither right-handed nor left-handed will converge to the right thing. So it was still wrong in this sense that it was a one-sided discretization, which my conjectures say the method doesn't converge to the right thing.
Well, no more questions. Let's thank the speaker once again.